Good evening and welcome to another Monday Night Calculus. My name is Curtis Brown and I am joined here again by Steve Kokoska and Tom Dick. I'm super excited to have these guys on this evening. We have some more questions from you, the audience, and we're excited to take some time here to answer those things. Before we get started, I do just want to prime the pump again and say that it would be so great to have your students join us in these sessions. We would love to have their questions flowing in the comments section and be able to have Steve and Tom answer those directly. I know these guys have tremendous amount of experience and ideas around the things of calculus, and in particular the AP exam. So both of them are experts in that space. And so I encourage you to take advantage of that, and your students to take advantage of these guys offering this time to ask them questions directly. I would encourage you to do that. Also, I will put out there one more time just a call for questions. So if you come across things that you would like to have these guys answer on a particular evening or a talk, feel free to email me. My email, I think, is in the chat box. If it's not, I'll make sure it's in there here in just a second. Allison actually will take care of that for me because she's awesome doing that. And so it's curtis@ti.com. Feel free to reach out to me and we'll make sure to get those questions in and Monday Night Calculus coming up. So without further ado, Steve, I guess you've got the first section tonight, so I'll let you take it away.
All right. Thank you very much, Curtis. Nice to see you and Tom once again.
Good to see you.
There were some great questions on the Facebook page this past couple of weeks. And Tom and I kind of figured that many instructors are probably teaching derivatives now and derivative rules. And so we might not get to everything, but we have a couple of, I think, good problems involving derivatives and involving a lot of the rules: quotient rule, product rule, chain rule. And we'll see if we get there. They're a little different. They rely upon tables and graphs. So let's take a look at this first one. This was sent to us by Sarah Strick, if I've got the name correct. And this is really a BC problem, but it's a great BC, classic BC type problem. The first thing you should notice in looking at this problem is that it is an improper integral. And I want to remind teachers, any students or teachers, remind your students that if your students see a problem like this, probably on the multiple choice section of the exam, it's incumbent upon them to recognize that this is improper. You know, there isn't going to be a little hint in the problem or on the margin. They've got to see this. And so that begs the question, why is this improper? Why doesn't the fundamental theorem of calculus apply here? So maybe we could leave that in the chat. Curtis, excuse me, maybe we could get a couple answers to that. You know, this is
sure. I'd love to be watching for them.
Okay, this is a pretty easy antiderivative. And so one might look at this and just say, well, I'll apply the fundamental theorem of calculus and I'll get capital F of B minus capital F of A. Why can't you do that? Well, you can't.
Just because, Steve, or what?
Somebody's going to answer that. Somebody's going to answer that in the chat.
Somebody is going to answer that. Gerald just said that his students are getting started with this kind of stuff. So
okay,
I think we got to.
Well, this function is discontinuous over its domain -1 to 1. And so we can't apply the FTC because it has to be continuous from -1 to 1. So it doesn't work here. And so in order for me to kind of illustrate a lot of the things I think that came up in the question on Facebook, I want to go back and take a quick peek at the definition of improper integrals of type 2. Now, I'm not going to read through all of this, Curtis, but I want to take a look at a couple of things. Let's take a look for just a second in part A here. It says that if f is continuous on closed A to open B, but discontinuous at B, and you'll notice something here. This doesn't say that it has to have sort of an infinite discontinuity, that is, as x gets closer to B from the left-hand side. It's not necessarily saying that the function is going off to plus infinity, but it's saying that it's discontinuous there. Then we define this definite integral from a to b as a two-part process. At least that's the way that I teach this. The first thing we need to do is we need to take this definite integral, and that's the way that a lot of students solve these on the AP exam. They start this by simply solving this definite integral, simplifying as much as possible. And then what they do is the second step is to evaluate this limit. Now, if this limit exists as a finite number, then okay, we say that this definite integral converges. All right, so we have a similar definition if it's discontinuous on the left-hand side. Now, the problem that we really have here is that we have a function that's discontinuous in the middle somewhere. And so the definition that we use, and I should remark there are other definitions, there are other ways to do this, but this is the most common, this is the way we usually do, is we split this definite integral up into two separate definite integrals, generally at this point here, C of discontinuity. And then what we need to do is to apply definition A and definition B to each of these parts. So we take a look at one of these definite integrals separately. If it's convergent, then we'll take a look at the second one. If it's divergent, we're done. We know that the original integral is divergent. So they both must converge for the original integral to converge. So let's take that information and go back to this problem. We need to split this up as a definite integral from -1 to 0, 1 over x, and 0 to 1, 1 over x. And I've drawn a graph here. And this to me is really kind of a cool problem here. There's lots of neat things I think going on here. What we in some sense want to do is find the area of these shaded regions, which almost seems like it's impossible. It's almost like I'm trying to take a fence and enclose a region of infinite extent. How can that possibly have finite area? It's kind of a weird idea. One of the things I think, Curtis, that was brought up on the Facebook page was, well, it sure looks like there's a lot of symmetry here. And it sure looks like, that these two areas should cancel out. And the answer ought to be 0. Well, not so fast. That's what it kind of looks like graphically, but you can't jump to conclusions here. You've got to go back, not unfortunately, but you've got to go back to our definition. So let's see what happens here. If we take a look at the integral from 0 to 1, I'm just going to take a look at one of those integrals, 1 over x dx. This is a limit as t goes to 0 from the right of that definite integral. And again, this is a pretty easy antiderivative, the log of the absolute value of x. Now, the way that I'm doing this is I'm sort of doing both steps here, writing both steps, but I'm working on the antiderivative. I'm leaving the limit out in front here. I haven't done that yet. So let's see, I got rid of the absolute value because, well, let's see, t is going to 0 from the right, so it's positive. 1's positive, so all right, log of 1 minus log of t. Log of 1 is 0, so that's equal to 0. And what happens to the log of t as t goes to 0 from the right? Think about the graph. It's going down to minus infinity. And so that drives this whole limit here to plus infinity. So I'm done. I took a look at one of those improper integrals, and it diverges. I don't have to do any more. That means the original integral diverges. So that's, I think, a very nice problem. There's some cool symmetry in there, which is kind of counterintuitive to what the answer is here. But the answer is that this original integral diverges. So that's a nice one to start out with. Tom, do you have a little technology here?
Yes, I do, Steve. I could
okay.
a little bit with that.
All right.
While we're switching over to Tom there, I just want to call out the folks who signed in from Mr. Gillis's class. I've got Angel and I've got Felix. I think I saw Felix scrolling back through the chat trying to make sure I don't miss anyone. I got two different Christophers that Christoph and a Chris that both joined. And Felix, that's exciting. So Mr. Gillis, hey, good on you. Super excited that you've got your students here and great for your students who have showed up. Make sure to interact and ask questions, respond to the questions that Steve asks. He's going to put some out there and do that.
Are we giving them extra credit, Curtis?
Can I give them? I can't give them extra credit.
Okay.
I mean, that's going to all be up to Mr. Gillis.
Okay, just checking.
And I hope I'm saying that right. So you can correct me in the chat if I'm wrong. But anyway, that's exciting. I'm really excited to have you there and welcome.
All right, Tom, what you got?
So I'm trying to share my screen here. I think I'm sharing the TI-84 screen. I'll look for some feedback from
Yes, sir.
you and Curtis. Okay, good enough. You were talking about improper integrals and just thought we might take a little bit of time to see what that looks like if you try to use your calculator on an improper integral. And so just using that example that you just had, Steve, I'm going to bring up the math menu, and down there at the bottom is the integral fn. And I think you had what, the -1 to 1?
Yes, sir. Mm-hmm.
And the function was 1/x.
Right.
And see what happens if we try to put the calculator tackle this improper integral. It has an interior point of discontinuity here. Aha. So
Oh no.
keep in mind that the TI-84 is actually always going to be using students can think of it as it's using some approximation techniques like Riemann sums. It's actually using things that are more efficient than that, but here it's encountered. It actually tried sampling the point x = 0 in its approximation, so it ended up with a division by 0, which it didn't like. Now here's something you might find interesting. I'm going to slightly edit this integral. And what I'm going to do is I'm going to change the this interval for our definite integral is symmetric around 0. And Steve, you called attention to that one could be thinking, well, don't those two areas somehow cancel out? One's being counted negative, one's counted positive. And we really can't do that. In part, we do need to split it up so the discontinuity is at an endpoint. But I'm going to change this interval so it's not symmetric about x = 0 and see what happens if we try to evaluate this one. Oh, we actually got another problem come up, but it was a different one.
Yeah.
Notice that with that unsymmetric interval, it ended up not actually sampling x = 0,
Right.
but it was running into problems trying to calculate that. It wasn't getting convergence of its approximations, and that's where it says, I give up, I can't do it. Okay. Now you might wonder, well, what if you gave it this was a divergent improper integral. What if we gave it an improper integral where it actually converged? So let's go back and try one more. Let me, let's see, I'll just do it from scratch. Pull up the math menu. We'll get our integral here. I'm going to integrate from 0 to 1 of the function 1 divided by the square root of x. And this again is an improper integral because it's not defined at x = 0. Still trying to divide by 0. But because that's at an endpoint, it'll be interesting to see what this does here. Ooh, we actually get a value back. Oh. What's interesting is there's some things I could kind of conclude from this, that is with that division by 0 at the endpoint, evidently, whatever method this calculator is using, it doesn't have to sample the endpoint. And so when it was doing these approximations, they were actually converging to a number and said, wow, this result looks pretty close to 2. I really want to caution folks, you don't want to take this, oh, this is telling me that it converges. It says, no, for its purposes, it was getting an answer that seemed reasonable. We'd want to do the actual limit analysis. And this is one where you actually get a convergence, a convergent improper interval. So I think sometimes people think, well, improper intervals are completely off base for a calculator. That's not actually true. If you have a well-behaved one that's convergent, you could actually get a pretty good approximation by doing the integration. But you can also see that not taking care, you might not get a result at all. Functions that are very slowly diverging are particularly problematic. So that's why we use this tool up here in connection with our calculator. All right, I'm going to turn it back over to you, Steve.
Okay.
Stop share.
All righty. Let's see, where did that go? There it is. Okay. Well, thanks, Curtis. This was Tom. That was really cool. I wanted to ask you maybe something you could just think about. You know, of course, on the 84, that does everything numerically. On a CAS machine with an improper integral, it's certainly possible that the CAS machine could return the exact symbolic answer if it's convergent. Is that correct?
That's correct. Yeah.
Which is pretty cool, which is really cool. All right, well, this is a second question that was submitted by Dorothy Buddy Rich, if I have the name correct. And I'm sorry, Curtis, I'm going to get too excited about this. This is one of my favorite topics. I really, really enjoy talking about this. I've thought an awful lot about this, probably too much, but this is really cool. I'm going to do a little bit of a content presentation. I'm going to do a couple of examples in here and see if I can get our audience to sort of buy into this. So this question revolved around intervals in which a function is increasing or decreasing, intervals in which a function is concave up or concave down, and the whole topic of endpoints. Do you include or exclude endpoints in these intervals? Well, in order for me to answer that question, I really need to go back to these definitions, so please bear with me.
So this is indoctrination is what it is.
Indoctrination, yes, sort of.
Okay. You're trying to get buy-in.
Yes.
All right.
Yes,
okay.
This is a booster shot, yes. So this is a definition for increasing or decreasing. And again, I won't read through everything with you, but just the first part of this. It says that a function is increasing, and to me, the important part of this is it increasing on an interval I. If for any two values, x1 and x2, with x1 less than x2, the value of f at x2 is bigger than the one at x1. And you can kind of picture this geometrically, that as you move to the right, the function is increasing, it's getting bigger. Okay, we've got a similar definition for decreasing. As we move to the right, the function values are getting smaller. And again, I'll say that this definition is given in terms of an interval, darn it, not a specific value. Now, when you teach this, I know your AP Calculus teachers out there, I know you also teach this increasing and decreasing test, and many of you probably even prove this. And it says that if f prime of x is greater than 0 on an interval, then we know that f is increasing on that interval. Notice this says, once again, on an interval. On an interval. It doesn't say anything about a specific value, and I'll just add a little bit down below here. This increasing and decreasing test doesn't say anything about, well, what's going on if you have a place where the derivative is exactly equal to 0. Okay. Let's put a little bit of this together. Let's do an example. Think about how you might present this on an AP Calculus exam. Let's find where this function, this polynomial, this fourth degree polynomial is increasing and where it's decreasing. Okay, so we all probably have our own techniques and our own styles for solving this. What I would do is find the first derivative, and what I would do after that is factor completely. I find that the quickest way to solve this kind of a problem.
Sure.
And then what I'm going to do is look for candidates, what I call candidates for extreme. The candidates for extreme values are places where the derivative is 0 or where the derivative does not exist. Well, this is easy. This is a polynomial. There are no places where the derivative does not exist. That sounds kind of funny, but that's the way that I would say it. And because I factored this in complete form, or factored it completely, I see the zeros here are -1, 0, and 2. Now, you'll see below this that I've drawn a sign chart. Many of you go, oh man, I can't use sign charts. Sure you can. You can use a sign chart. I encourage my students to use a sign chart, but it's not enough. It's not sufficient justification, but there's certainly no penalty for using a sign chart to help you understand what's going on. Now, I probably put in a couple of extra symbols here that are necessary, but the way that I draw my sign charts, I put tick marks in here where the derivative is 0 or does not exist. And we could spend a whole couple of hours on variations here. Variations where there's omissions in the domain, where the derivative doesn't exist, and all kinds of things. But this is a straightforward one. So what I do after that is I either pick a specific value in each interval or kind of argue in general. And that's the way that I've always done this. That's the way I learned it. I kind of look at this factored form and I argue in general in each interval, will the derivative be positive or negative? So that's how I got these signs in this row. Okay, and I put corresponding arrows down below. I know because of that increasing or decreasing test that the function is decreasing, increasing, and so forth. Let's put this all together. This sign chart tells me that the function is increasing on the closed interval, -1 to 0 closed, closed 2 to infinity. Decreasing, -infinity to -1 closed, 0 to 2 closed. Now, I know somebody out there is already writing in the chat, wait a minute, this is a contradiction. How can it possibly be that you could include 2 in that interval and also 2 in that interval? And here's my response to that. We don't have a definition for a function increasing or decreasing at a specific value. We only use the definition, is it increasing or decreasing over an interval? And if you think about that definition, if you apply that definition, as you move left to right, is the function increasing on that interval? You bet it is. Can I pick any 2 values in that interval? And as I move to the right, this one's bigger than the one on the left? You bet. Is the definition of decreasing true on that interval? Yup, you bet it is. Now, we were talking a little bit before we came on the air tonight. When I was on the test development committee, I always argued that we should never ask a question on the exam that says, is a function increasing or decreasing at a value? Now, unfortunately, there are still a couple of problems like that, often in context. But I struggle with that. I don't really know how to answer that. Now, Tom has a good response to this, which is that we can talk about the rate of change at a specific value. But we can't really talk about increasing or decreasing at a specific value. So all of that aside, how the devil do we score this? Well, on the exam, in general, we don't worry about the endpoints. They don't matter unless a student includes a value where the function is undefined. So for example, if a student told us that the function is increasing on the interval 0 to 3, and the function was undefined at 3, they would not get credit. And the other thing that we don't allow is a student to tell us or put a closed symbol on infinity. And I'm sorry about this, Curtis. I put that in red. I don't like to do this. I don't like to write wrong things here. And I get in trouble sometimes. I apologize. I forget some people are colorblind and can't see that red. But that's a bad thing. You don't want to put a closed symbol on infinity.
I appreciate you putting it in red, just some kind of indication, but yeah, you're right.
It's wrong. Okay.
It's hard
It's
for,
wrong. Yeah.
right. It's wrong. Maybe we should put a little note in there. This is wrong.
All right.
By the way, if anybody is, and I think we answered this question before the chat started, but if you're looking for this printout or these notes that Steve has pulled together, we'll be posting these in the bulletin board post tomorrow morning. We'll make sure that that bulletin board post gets updated with this information so you can download it here. And then also I'll make sure that or Allison is going to put that in the chat here in just a second.
Fantastic. Thanks, Curtis. So we've tackled increasing and decreasing. What about concavity? So again, I have to go back to the definition. And here's the definition I think that is most common. It says that F is concave up at A. I'm going to circle that, at a specific value, not in an interval, but at A, if the graph of F is above the tangent line for all X in a neighborhood of A, but not necessarily equal to A. All right, so we've got a similar definition for concave down. Again, this is defined in terms of a specific value, not an interval. Let me draw a couple of pictures here, if you don't mind. Here's a picture of a function f, and at the value a, it is concave up. And the reason is because I draw the tangent line to the curve at a, and I can get a small neighborhood or a neighborhood of a, so that the function is entirely above that tangent line in that neighborhood. Okay, except possibly at A. Similarly, over here, if I draw the tangent line, the graph of F is below that tangent line in that neighborhood. So now what happens with a situation like this? Suppose we have this function y equal f of x, and I draw the tangent line at A. You can kind of see this as maybe, think of this as kind of like y equal x cubed shifted a little bit. I draw the tangent line in there. This one happens to be horizontal, and I cannot find a neighborhood so that the graph is completely above the tangent line or completely below.
Right.
Oh, the way that I interpret this definition is that means there is no concavity at that point A. Beautiful. So let's take that definition, look at another problem here real quickly. Let's find the concavity, intervals of concavity here. And you know what? While we're at it, let's find the points of inflection. So I do this similar. I find the first derivative and then find the second derivative and factor completely. I'm going to find candidates for points of inflection. I used to say nominees to distinguish between candidates for extreme values, but people thought that was too political. So now I say candidates for points of inflection. Places where the second derivative is 0 or where the second derivative does not exist. Here's a similar sign chart. And here's what my intervals look like. I would say now that this graph is concave up on the interval minus infinity to 0, and 2 to infinity, concave down 0 to 2. I am not including the endpoints here. And the reason is because if I were to draw this out, I would have no concavity at either x equals 0 or x equal 2. Again, I think about the definition, and I wouldn't be able to draw a tangent line and get concave up or concave down. So here's an illustration. Here's a graph. Oops, I'm sorry about that, Curtis. Here's a graph of this function. And while we're here, I'm going to give you a definition of this in a minute. But the inflection points here are 0, 0, and 2 minus 16. What's an inflection point? An inflection point is a point on the graph where the graph changes concavity, evidenced too by my sign chart. So that's pretty cool, but let's get a scoring conclusion here. How do we grade this on the AP exam? Now look, this could change certainly, but this has been pretty standard over the last, I would say, decade. So inclusion or exclusion of the endpoints don't matter unless the student shows us a contradiction. You can't include infinity. And you cannot include points where the function is undefined. Remember that a sign chart is not sufficient justification. Boy, in my opinion, it's extremely helpful, but you have to interpret that sign chart. What does that mean? You have to write a sentence that interprets that sign chart. So written justification is necessary. All right, thanks, Curtis. One more page here, and I'll turn it over to Tom, I think. Yeah, one more page here. So let me kind of conclude here with a definition of an inflection point and remind people of one issue here. A point P on the graph of f is an inflection point if f is continuous there, and the graph changes from concave up to concave down or vice versa. Now, again, that's the definition that I use, and I think that's a pretty standard definition, but there is another one that appears in some calculus books. And that is, you cannot have an inflection point unless the graph of f has a tangent line there, has a derivative there. Now, I don't use that one because I think it's certainly possible to have an inflection point on a graph, yet there's no tangent line there. The graph changes concavity there. So in my mind, that's an inflection point. But I want you to be aware of that. And I want you to know that as they write the exam, they are sensitive to that issue and would never put a student in that position to have to decide between a couple of definitions. Okay?
So if a graph is not differentiable at that point for some reason,
I don't know if I can.
And yet we change concavity.
Yes, I don't.
Maybe we have a sharp point. I'm just trying to clarify and make sure, you know.
Something like that, Curtis. If you can see that. Something like that.
And there's a sharp point.
There's a sharp edge corner there. To the left of A, it's concave up. To the right of A, it's concave down. There is no derivative at A. There's no tangent line at A. But my response is there is a change in concavity there by my definition. There is an inflection point at A.
Right.
Okay.
But just to be clear, the exam is really, the exam writers are not out to get you. The intent is definitely not that.
Yes.
And so they're going to avoid this.
You would never, I would bet you'll never see them put a student in this situation and force them to decide. Yeah, absolutely. Right. Absolutely. All right, so let's do this. Take a quick closer look. I like this, as you know, Tom and Curtis. Here's what we've sort of seen, and here's a quick procedure. If f double prime of A exists and it's not equal to 0, we know the concavity because we know that f double prime must be positive or negative. We know the graph cannot change concavity at that point. We know that f double prime of x can change sign only when the second derivative is 0 or doesn't exist. So the concavity test in my mind is we have an inflection point only where the second derivative changes sign. And I can use a sign chart for the second derivative to do that. And I do that in my classes. So this is sort of a quick procedure that I would use if I had to determine inflection points. Find the inflection point candidates. So these are values in the domain of f where the second derivative is 0, or doesn't exist. And then I screen these candidates. I check for a sign change in f double prime. If there is a sign change, it's a point of inflection. If there is no sign change, there's no point of inflection. So I think that's a lot of cool material, a lot of cool content. We really haven't had an opportunity to talk much about content here in these sessions, Curtis. That was a great question. I appreciate that being asked on the Facebook page. And I hope that clarifies where we're coming from and where the AP exam committee is coming from too. Tom.
Yeah, I think that's helpful. Tom, do you have anything to wrap up on that?
No, not on this.
Yeah. No, okay, good. Okay, very good. Thanks, Tom. I'm going to come back then. And I think, Curtis, you mentioned something about, somebody had a question or two about derivatives.
Yeah, I think, well, I mentioned earlier we started talking about integrals and things. And so, but you've kind of done a little bit with derivatives here. I think we've got some more going on that. So.
Okay. Well, I think, again, that many teachers are at the point in the class where they're doing derivatives, they're looking at a lot of rules. And I think this is, I've got a couple of, I think, really good problems. And we're actually going to leave people with a question tonight on one of these, Curtis. This one is numerical or tabular, and we frequently see problems like this on the exam. So we know that P and Q are differentiable functions, and we've got some values for these functions and their derivatives at specific values of X. I've got a new function F defined down here. You'll love to see these on the calculus exam, on the AP calculus exam. P of the square root of Q of X, yikes, I want to find F prime of 5. And H of X is Q of X divided by X, and I want H prime of 4. So here we go. Very typical sort of a problem. The first thing I'm going to do is find F prime of X symbolically. Now, just as an aside, we know that a lot of your students are really good. They're terrific. And a lot of them will solve this problem by going directly to find F prime of 5 without this intermediate sort of symbolic approach here, or answer, or expression. I would like to suggest that they should do that given time, because in the event that they would make a mistake, not that they would, but if they make a mistake, they're more likely to earn some partial credit if there is this sort of extra step in here, that symbolic expression. So in order to find the derivative of F, I've got to use the chain rule. I start at the outside and work my way in. P prime of the inner function, which is the square root of Q of X. The next derivative is Q of X to the 1/2. So yikes, that's 1/2 Q to the minus 1/2 times the derivative of that inner function, Q prime. And here we go. I'm going to find F prime of 5. Jeepers, let's see if I've got this right. P prime of the square root of Q of 5. Wow, I plug in X equal 5 there. Let's see if I've got some of this. Q of 5, did I get that right? Looking up there, Q of 5 is 16. Yeah, I've got that one. Okay, and Q prime of 5 is 7, so I've got that. All right, now I've got to find P prime of 4. Let's see, where's that? P prime of 4 is 8. There we go. 8 times an 8, a little bit of canceling, and finally, after all of that, I got a 7. That's a really nice problem. That
is a nice problem, Steve. And I'm just going to point out that Gerald just reached out, Mr. Gillis reached out and said that these are great problems and that he just did some of these in his class. And also, I will tell you that this session is functioning like a review session for those guys that joined us this evening. So good on you, students, for being here. That's awesome, because it sounds like you've got a test coming.
All right, here's the second one. I need to find the derivative of H. I need to recognize that that is indeed a quotient. I've got to use the quotient rule. So let's see, the derivative of H, or bring the denominator up, X times Q prime minus Q of X. I'm sorry about this. I probably should have, for clarity, put in times the derivative of the denominator, which is 1. Now I'm going to plug in X equal 4, and let's see, do I have everything right here? Q prime of 4, oh, I got to look back up there. Q prime of 4 is what, 2? Did I get that right? Yeah, that's right. And Q of 4, I believe, is 4. And a little bit of simplification, and that's 1/4. And let me remind you something here on the AP exam. You know, I went ahead, and this isn't too bad, and I simplified to 1/4. But under the pressure of a high-stakes exam, remember that you don't have to simplify a numerical final answer. And so you could, students, if you want, you could leave your final answer just like that and get full credit. Now, not in my class.
I was just going to ask that question.
Not in my class, but on the AP exam, you can indeed do that. Now, not here. Not here. That's not far enough. In a tabular problem, you've got to go to the table and draw out those values.
Tom, I saw you laughing there. I assume that would not be okay in your class either. You need to go ahead and finish out the arithmetic.
Actually, I'm okay with them not finishing out the arithmetic. I'm okay. Not. Steve and I were like good cop, bad cop.
This sounds like maybe a question for the chat too. Sounds like maybe we ought to prepare some folks out there for their classes, see if we can get something started as a discussion. Do you finish the arithmetic or not?
Good question. All right, well, let's try one more here, Tom, and then I'll turn it over to you. This is another problem that involves derivatives, but this one's graphical in nature.
Ooh.
So this has the graphs of f and g that are shown in the figure. And I'm going to define three separate functions. And I apologize for this, Curtis. I'm going to kind of go back and forth here, shift a little bit on my screen here. I've got a function u, v, and w, and I want to find each of these derivatives if it exists. And again, I apologize, Curtis. I probably should have done these in a little bit different order. I probably should have put B last. I'm going to look at A and then C, and then I'm going to come back and look at D, and I'm going to leave an open question, okay? So here we go. How do I find u prime of 1? Well, all right. I have to use the chain rule. So let's see. I start at the outside and I work my way in. That's f prime of the inner function g of x times the derivative of the inner function g prime of x. And now I want u prime of 1. So I'm going to plug in x equal 1. Well, let's see. How do I do this? Well, let's see, g of 1, I'm going to find that by looking at the graph. And Tom and I discuss this frequently. You know, we're going to assume here that the graph is pretty accurate. And if it looks like g of 1 is 3, well, then darn it, it sure as heck is 3, okay? So I have to find f prime of 3, and I have to find g prime of 1. So, okay, here's a question for the chat, maybe, Curtis. How do you find g prime of 1? So let's see, g of 1 we know is 3, it's up there, but how do you find the derivative there?
Hey, this is one I think I could manage.
Okay.
I mean, it's a linear function.
Right. So what do you do?
And it appears to me, although I'm going to have to make an assumption here, that you've got a point at 0, 6.
Absolutely. That's correct.
And another one at 2, 0.
Sure.
So I can probably find the rate of change of that function.
Very good. So I'm going to take a look at the slope. Excellent. I'm going to take a look at, whoops, I'm sorry, 6 minus 0, the change in y divided by the change in x. And I think if I've done everything correctly there, that's a minus 3, and that's where that came from. How do you find f prime of minus 3? Well, darn it. You do it in the same way. Well, wait a minute. What was that? F prime of 3. So here's 3. So how do I do that one? Well, okay, it looks like it goes through the point 2, 4. And indeed, it goes through the point 6, 3. And so I think I've got a slope there of minus 1/4. I do a little bit of arithmetic, and that value is 3/4. That's a nice question, too. It not only uses the chain rule, but it asks the student to find these values using the graph and to think a little bit, how do you find that derivative from the graph? Now, I'm going to skip B for just 1 second. I'll come back to that in a minute. Let me just...
We had one of the students reached out and answered the same thing I did about putting in the slope. So that's awesome.
Very good.
Coming up with a slope. So sharp answer there.
Excellent. Well, this one is similar. It's got a lot of g's in it. I start at the outside, g prime of g of x times the derivative of the inner function g prime. And it is indeed similar. And we're going to post this one, so I won't go into this one in gory detail. I think I got an answer there of -2. I think that's a similar question, but very good practice for those students who have a test coming up. And let's take a look at B. So I want to find v prime of 1. I'm going to start out by finding v prime of x. That's g prime of the inner function f of x times f prime of x. I'm going to plug in 1. I'm going to take a look at this value first, f prime of 1. Let me sneak back up to the graph here. Where is that? Well, let's see. Okay, I can use the same technique here. I think I can see the slope there just by looking at that. When the rise is 2, the run is 1. So it has a slope of 1, the derivative there, pardon me, has a slope of 2, the derivative is 2, yep. So that's good. But what about g prime of 2? What's going on here?
Whew.
How do we do that? What do we do there?
I'm going to let one of the students answer that one.
Yeah, what do we do there?
I think we got a response.
Okay.
Oh, we also had, so just heads up, we did have a question about that improper integrals that you started the session
Yes.
with. I just want to make sure we point that out, that we started that,
Okay.
started our evening with that. But that's okay. I'm looking to see in the chat. I thought I saw something come up, but maybe not quite. Oh, here we go. Yeah, Angel says does not exist at a corner. So the derivative.
Very good.
We've got a problem there because we've got a sharp
We've got a problem. Or yeah, it doesn't
right
exist.
here in River City.
So let's see. G prime of 2 does not exist because on the graph there's a sharp corner. And this is something that we kind of talked about. And Tom did a nice explanation of this graphically. You know, we've got the sharp corner. The more we zoom in there, we can't get rid of that sharp corner. The function is not smooth there. There's no derivative there. It's not locally linear. And so the tendency here would be to say, well, wait a minute. G prime of 2 doesn't exist, so that must mean that V prime of 1 does not exist, but not so fast. Remember back a couple of sessions ago, we did a problem similar to this. You cannot use the chain rule here. This is tricky. You cannot use the chain rule here because the assumptions are not satisfied. One of the assumptions is that this derivative must exist. So since it doesn't exist, we've got to use some other method here to determine this value V prime of 1. Now this is tricky. This is unlike the one that we did a couple of weeks ago, and I'm going to give you one suggestion as to what the answer is, and then we're going to leave this as an open question. Now, what I did is I actually wrote analytical expressions for both F and G. You know, they're made up of straight lines, and Tom has done some great stuff showing us how to define piecewise functions on our calculator. And so I defined a piecewise function for F and a piecewise function for G. And then I defined the composition the way that it was given here. And what was V again? I apologize. It was, I think, G of F of X.
V was G of F, yeah.
G of F of X. And I graphed G of F of X. I graphed this function V. And I want to know here, I think it was what's going on at V prime. What is V prime of 1? Well, a student just answered this and told me, well, if there's a corner there, it's not differentiable. And so this graph suggests at least that V prime of 1 does not exist. So now the open question is, how do you show this analytically? How would you go about convincing me? This graph, you know, calculators lie, but this graph certainly suggests that the derivative of 1 does not exist. How would you show that analytically? And we'll leave that as an open question.
I think Wanda Burns may have given a suggestion.
What did she say?
As to how they could get there.
Okay.
But I'm just gonna
leave that.
leave
Okay.
that up there too.
All right, Tom, can I pass it over to you?
Sure. Yeah.
Okay.
Yeah.
All right, there we go.
So I'm going to share my screen again. This time, though, I'm going to look at TI-Nspire as a platform.
Cool.
And this is something that I thought was related to one of the main themes tonight, and it's the mean value theorem. You might think, well, how is that related? Well, it turns out that I believe this is the theorem you need to come up with that increasing decreasing test.
Correct.
Or Steve mentioned, where if you do know that the derivative is positive on an interval, then you can conclude that that function has to be increasing on that interval. And similarly, if the derivative is negative on that interval. Did I say increasing before? But if the derivative is negative on an interval, the function must be decreasing on that interval.
Yeah.
So mean value theorem, some people say that's the one theorem that if you just saw a picture of it on the board, you could identify what theorem it is without any words. So, but we're going to look at it in kind of a dynamic fashion here. So let me go ahead and show you what we've got here. Let's see. So what I have here is a graph of a function shown in red. And I've got a couple of x values at a and b. And you can see that this dotted green line it's actually the slope segment. It's the secant segment that connects the points on the graph that correspond to a comma f of a and b comma f of b. And down here at the bottom, it's actually reading out what the slope of that secant segment is. This is actually dynamic. I can move point A around and see that segment. And if you look down at the bottom, the slope is changing also. And I can move, oops, I should actually grab B here, move it around. And this little toggle up here at the top, all it does is actually, I can ask for this to show me, are there any points in between A and B at which the tangent line is parallel to that secant line? That's the query is. And so when I click on that, it shows me, okay, for this choice of A and B, there's actually two different places where the tangent line is parallel to that secant line. And what's kind of cool about this is actually a dynamic picture still. If I move A to new locations, oh, look at this. I picked up a third one. All right. So it's showing me there's three places. Yes, Curtis.
So I'm going to ask it now. I should probably have waited, but I'm going to ask it now anyway. Would you be willing to share this file with me so that anybody who wants to see this, if they've got TI-Nspire software, we'll send them this file?
Absolutely. And in fact, this is a file that's taken off the Math-Inspired site. So this is in that repository of...
this particular one?
Yeah. Sure enough is. Yeah.
It says MVT 1018. I just
I labeled it with today's date just so I would know to retrieve it easily.
Okay, but this is the one
that's on. If you look up mean value theorem for derivatives, this file will be there. Yeah.
I'll make sure and get that link in the chat here in just a second.
Now, what the mean value theorem guarantees is if you have a function that's continuous between A and B, and it's different, including A and B. So it's on the whole closed interval from A to B. It's continuous. And it's differentiable in between A and B on the open interval from A to B. Then you are always guaranteed to find at least one point in between A and B where your tangent line will be parallel to your secant line. And here we can see that you could actually have more than one. I'm going to move A. Here I moved A to a place where we have only one, where they're parallel. Okay. Let's take a look at another picture. Okay, here's another graph, kind of interesting graph. Again, I have this secant slope. And you might ask yourself, just eyeballing it, can you see, is there at least, let's see, this function looks nice and continuous. It looks like it's smooth, it's differentiable in between A and B. Can you see the spots between A and B, or it might be spot singular, where our tangent line would be parallel to that secant line? And you might be thinking, well, maybe somewhere around up here, down here. I'm not sure in between here. This looks like it, I don't know. How many places do you think, Steve?
17. No, wait a minute. I'll go with 3.
3. Oh, there's only 2. There's only 2. But let's see. Let's see if we can move A to places where we get a few more. There's
Ah,
three
I was
there.
going to say, you need,
That's
you
where I
need,
thought. Oh,
you need the difference between A and B to be relatively flat in order to get 3.
Now I'm actually going to move A over to a place where the graph crosses the x-axis. So that's a 0 for my red graph. And let me move B over to a place. It looks like there's another 0 here. Notice there, this is a special case, the mean value theorem, sometimes known as Rolle's theorem. And it says, well, if you have 2 zeros for your original function, and again, needs to be continuous on that closed interval and differentiable on the open interval, there has to be at least one spot in between where the tangent line would be horizontal, where the derivative would also be 0. Here we can see there's actually 3 spots there. Now, the mean value theorem is, it's one that students are expected to know in AP Calculus. It's a very important theorem. You're not asked to, on an exam, to regurgitate a proof of the mean value theorem. I think it's an accessible theorem. I certainly have my students try to understand it, but the thing that is asked for on the AP exams is for you to be able to use the mean value theorem and know when it can be applied and when it can't be applied. And
to justify that?
Well, you need to check that the hypotheses that it relies on have been satisfied. So I was making a big deal that my function had to be continuous on the closed interval and differentiable on the open interval. Those are the things you have to check and say, hey, I've checked that these are true, therefore I can use the mean value theorem. That's the kind of language that's expected on the exam.
Interestingly enough, Dennis Donovan says he used this this week in class. And he says by the end of the session, his students are telling him the conditions of the MVT.
Excellent.
And that's, I think, the power of that dynamic piece there, right? You've got this and the students are able to play with it. And I will say, Tom, I just checked and looked at I downloaded the TNS file that's up on the internet. It looks like you've made some color updates and things here.
Okay, so there may be an older version. And
yeah, I think
Steve and I are going to be looking into this, updating some of these files.
Looks like you've polished this one.
Okay.
Well,
so here's an example.
We can share this for sure.
Sure. Yeah. Here's an example of a graph that illustrates why those conditions are so important. Here I'm going to see, well, between A and B, are there places where the tangent line is parallel to the secant line? And sure enough, there is. There's one spot here. But I'm going to move this point A. Let's see if I can grab it. There we go. I'm going to move it a little bit further to the right. Oops. Oh, something strange has happened. I'm not sure what I just did there. I think I somehow inadvertently changed the scaling. There we go. Okay, so I undid that. So notice here's a place where the secant line, and there's no places in between A and B where there's a tangent line that's parallel to it. So, and I didn't forget to toggle here. I toggle back and forth. There's just no tangent line. And as we look at it visually, you can see, well, yeah, no, there's no place here because this is negative slope and this secant line has a positive slope. And when I get over to here, well, these slopes are much more steep, much more positive. But it's this place right here where that violates the hypotheses. We've got a spot where the function whose graph is red is not differentiable. So there's a point of non-differentiability between A and B, and that violation kind of throws out our chance to apply the mean value theorem. And we can see it doesn't guarantee a tangent line because we haven't satisfied the hypothesis. And that's really on the exam. Those kinds of situations are sometimes given to students where there's a function that doesn't satisfy the mean value theorem. And they have to recognize that they can't use that. They'll need to draw on some other tools that they're needing to, some conclusion about the tangent line. Steve, I'm going to pass it back over to you, I think.
I'm good. Curtis?
Yeah, I think this is a good place for us to kind of wrap up. So, wow, that was really good stuff tonight, guys. Thanks for the questions. And thank you also to everyone out there interacting in the chat. Thank you to Mr. Gillis and your students for joining us this evening. That's fantastic. I'll be looking for an email from you this evening. That'll be a really good thing. And also, just one more plug. Again, we're going to be doing this in a couple of weeks. And so I just encourage you to join us again here on November 1st. Is that right? November 1st? That is right. Okay, so we're November 1st. We'll be doing this one more time. Please email me, Curtis at TI, if you've got questions that you'd like to see Steve and or Tom address via technology and Steve sharing his expertise from the scoring. And then certainly we'll be monitoring the Facebook page for more questions and things. But again, I can't overestimate it, emphasize it. I just want to encourage you to have your students come. Maybe Mr. Gillis' class, you can give us a testimonial at the end and encourage other students to join in. I think it's certainly worth it. Anyway, thank you, Steve and Tom, for your time. Thank you, Allison, for running the chat and the background. And we'll see you guys in a couple of weeks.
Great. Thanks.
Bye-bye.
Night.